This is Physics 2211, Lab 4, Oscillations, by me, Otto Abdu. Here's the introduction for the lab. The purpose of this lab is to analyze the motion of a real-life oscillating mass system and compare it to a computational model of the same system. Tracker is the application used to analyze the motion from the video we got, and GlowScript is the application used to create the computational model. Before we go into the details of this lab, I will say that by the end of the lab, we will see that the energy of the system remains constant throughout, as seen in both the computational and real-life models. We can attribute this to the energy principle, which we'll go more into detail in. There are two fundamental physics principles in this lab, Newton's second law and the energy principle. The first, Newton's second law, relates the net force on an object to its change in momentum. This can be seen by this equation here on the left. In the case of this lab, as we see the different forces act on an object, we will see a change in momentum and also velocity because of it. For the second equation, seen here on the right, the energy principle, it relates to the change of an energy of a system to the work done by the surroundings of the system. In our case, we took our system to be the Earth, spring, and mass, so there are no forces acting on our system from our surroundings. Because of this, we should expect no change in energy in our system. The model used to track the motion of the object from the real-life video is called Tracker. Here we can see our initial conditions of our object. This mass, tied to the spring, is kept at a point about negative 1.1 meters to the left and down negative 0.6. It also starts off with a velocity of 0. From here, we track the motion of the object using this application. We can see the x position over time and y position over time on the right in these graphs. Here is GlowScript, the computational model which we then compare to the analysis later on. The graph on the right computes the change in each individual energy and also plots the change in total energy. The model above it is also made to match up with the data points from the analysis video, but we will see that it doesn't exactly do this. Here are the results from the comparison of the two models on the right. We can see that the x and y positions generally match up, but they are slightly off. These differences could be attributed to many things. One example is forces that were not accounted for in the model, such as air resistance that the object faces when moving. This wasn't included in our system, so this means that there would be a change in total energy possible. Another possible cause for these differences could be human error when I was doing the tracking. I may have not placed the tracker at the exact same spot on the mass every time, which could lead to these discrepancies. As for the graph on the right, we can see that though the different forms of energy change as the system moves, the total energy stays 0 throughout, which adheres to the energy principle. So, what does it mean? To answer the question if the energy principle is satisfied, we say it is, as we see that though the different forms of energy change, they always result in 0. This makes sense as there are no forces from our surroundings acting on our system, so the total change in energy in the system should be 0 according to the energy principle. For the next question, we are asked to estimate the period for the oscillations of x and y. To do this in the x direction, I took the total number of revolutions in the x and got 5.6. I then divided the total time 9.5 by 5.6 to get the period of 1.696 seconds. I did the same steps for the y direction, using the number of revolutions in the y directions to get 1.461 seconds. To see how this would affect the motion, we then find the new k value of the spring given these periods. We know that the initial value of the spring is 6.8, which is what we got from the system before, but if we were to instead use these estimated values, we would have gotten very different results. Thank you for watching.